Good day, everyone. Welcome to my channel. My name is Tandy, and in this lesson, we're going to be talking about electric circuits. So, this is aimed at grade 12 learners who are doing physical sciences. It can be used for revision, exam preparation, or if you're looking to learn a couple of basic, yeah, some basic stuff about electric circuits. So this is part two or the second video that I'm doing on this topic. In the first video, what we did was my screen appears to be frozen. Yeah, so in the first video that we did, and I will leave the link below, we spoke a little bit about electric current, potential difference, resistance, up to Ohm's law. So that was the first part of the video, and like I said, I will leave the link to that video in the description below. In this video, so this is video 2, this is part 2, we're going to be talking about resistors that are connected in series as well as those that are connected in parallel. And then part 3 will be posted the video. I'll post the video about that after this one, and the last video that I will do on the topic is then gonna be just a few examples, perhaps from previous question papers that we're gonna be doing with you, just to reinforce that knowledge that we have learned in the previous videos. So let's get into it. So like I said, the first video I've already spoken about this, and this is part 2 of it. If you didn't watch it, I would suggest that you watch it because I will keep referring to it a lot. So yes, in this video we are going to be talking about resistors that are connected in parallel as well as those that are connected in series, and then you will get to see how the current, the potential difference, as well as the resistance of the entire circuit is affected by those configurations. So yeah, let us start. So I'm going to remove my face from here, so you'll just be hearing my voice from this point forward. And the first thing in this video that we start with is resistors that are connected in series. So like I start here, I'm going to start here at the bottom. So here you have an image of an electrical circuit. So you have a battery with a potential difference of 36 volts, and then you have a resistor, and then it has so R1 is the resistor. It has a value of 2 ohms. You have a second resistor here. It is R2 with a value of 6 ohms, and then you have a third resistor which doesn't have a value. So I took this from a question, and they were asking the learners to determine the value of this resistance. So this is how resistors that are connected in series would look like. So you see that, or if you look at them, they all seem to be on the same line, and I'm just saying that very carefully, but if you look at them, it's like they're on the same line. So if for example you were just to stretch this thing out, to pull it apart, you would have, let's say, the positive terminal of that battery here, which is this part here, and then you have that line or the wire, connected wire, and then you have your first resistor, and then you have your second resistor there, and then you have your last resistor, and then you have the negative terminal of the battery. So it's like if you were to stretch it out, all of them can just be following each other, then they can all be on the same line. There's no branching between them. There's absolutely none of that. So they're saying resistors in series are consecutive elements in the sequence of a circuit. So that is the circuit, and they are just consecutive elements, this one following the other, no branching. And yeah, there are no branches between them. So for n resistors in series, so our for us in our case we have 3 resistors, so our n will be 3. So for 3 resistors in series, the total resistance in the circuit is going to be nothing but Rs, the value of R1, the value plus the value of R2 plus the value of R3, and then you have the total resistance in the circuit. So that is how you calculate it if those resistors are in series. And then they go on to say, for n resistors, in our case n is 3, so for these 3 resistors that we see in this circuit, the potential difference is split across the resistor. And normally they use a term, they say resistors that are connected in series are potential dividers. So if, for example, you were to say, okay, I want to determine the potential difference between the total potential difference in this thing. So you'd perhaps connect a voltmeter here. Remember, a voltmeter is that device that measures the potential difference. So you're connecting it between here on the battery, and there you are. So you're connecting it there by the battery. So we have that V. So we have that V. That value that you get there, it would read a value of 36 volts. So that is what you would read. And then they saying that, let's say for an example, you connect another voltmeter here to measure the potential difference at this resistor. You connect another one here, and then you connect the last one here. So you have now voltmeter here, V1, V2, voltmeter 2, voltmeter 3, so V3. So if you were to get the value, you get the value here, you get the reading here, you get the reading here. The total that you would measure here for the total potential difference here, it will just be the value here, the value plus the value here, plus the value that you will get here at the third thing. So for resistors that are connected in series, the potential is split across them. So it's like this potential here that is provided by the battery is split across this resistors, depending on the size of the resistor and how much work needs to be done. So a bigger resistor will require more work to be done, so there will be a lot of energy transfer or a lot of work done there, so the potential difference there will be higher. So that is it. But then interestingly, for the current is the same. So remember, when we talk about current, we're talking about the rate of flow of charge. So if we have charge flowing here, it's the same charge that is going to be flowing here. So it charge flows at the same rate between all of these resistors that are connected in series. So hence the charge is the same as the total, the current is the same as the total current in the supplied by the battery. So you have the current being the same on this resistor as well as in this resistor, and as well as on this resistor. So remember, for resistors that are connected in series, they are potential dividers. They divide the total potential that is provided, that is supplied by the battery, but the current between them is essentially the same. So to explain this a bit further, we can use the law of conservation of charge. So they saying that charges are not created or not destroyed. So that means that the charge here, the rate at which the charge passes from here to this point here is the same, making sure that the current is so this is consistent with the current being the same throughout this resistor network. So you don't have a different charge here, and then afterwards you have a different charge. That charge, that flow, that rate at which the charge flows is the same, because no charges are being created or being destroyed. And in terms of potential difference, why these resistors are potential dividers, why they divide the thing, you can think about the law of conservation of energy, which stipulates that energy isn't created or destroyed but transferred through work. Remember, to move this charge from here, from point 1 here to this point, work must be done. The same thing here, work must be done, more work must be done. And then if we calculate the total work done to move this charge here up to this point in our circuit, then it makes sense that we just add all the individual work, total it up, all of the individual work that we did here, here, and then we get the final VT, the total work that is being done. So this, as the statement says, it says the total work done to move through this network of resistors that are in series is nothing but the sum of the work done to move through each individual resistor. Hopefully that is clear. If it is not, please do not hesitate to leave your question, or if you want more clarity, I'll be happy to answer any of your questions. So, and then we go to the second part. So the second part is resistors that are connected in parallel. So a parallel resistor network, that is what we're talking about. So in that setup, normally this is what we will have. I don't know why it keeps doing this, but just skipping pages. I click once, it's and then it skips like 2 pages, but that is not a problem. So yeah, so normally this is how they are represented. This is a very simplistic electrical circuit showing 2 resistors that are connected in parallel. And now let's do the same thing that we did for the ones that are connected in series, and we take that positive terminal of the battery, and then we have also here the negative terminal of the battery, and then we put this as the first resistor. So that will be R2 from our circuit. But then you realize that for us to be able to draw the second resistor, there has to be a sort of a branch. It branches into another branch now, where we can be able to connect the second resistance. So there you are. So you see, I have 2 branches now, not 1 branch as was the case with resistors that are connected in series. So now in this case, but they can be multiple branches. They can be from 2 up until, yeah, I don't know, but it can be multiple branches. And even on these branches, you can find that you might have another resistor here, but still these 2 would be, there would be 2 branches. So yeah, so that is it. So here we would say this will be R2, resistor 2, and this will be the first resistor, which is resistor 1. So the value is 2 ohm for resistor 1, and the value is and then if you were to put a voltmeter here, something to measure the potential difference between the terminals of the battery, you would get that value of 12 volts. So now for parallel thing, you see they talk a lot about the branches. So they're talking about the branches, and they say for n number of branches of resistors in parallel, the total resistance can be calculated using this equation. So if a question says calculate the equivalent resistance, calculate the total resistance, here you will have to use this equation, 1 over RT or RE equal to 1 over R1 plus 1 over R2, and then you will have to do a little bit of mathematics there to make this to be the subject of your formula, and then you will get the total resistance. And for now, they're saying for n branches of resistors in parallel, the potential difference is the same throughout. But let me first start with the current. So in terms of the current, let's go here. Let's go to the yes, to our schematic here, our image. So you see that there is current flowing from the positive, conventional current that is flowing from the positive terminal throughout. And then, but through, when we saying the conservation, the law of conservation of charge, it says that charges are not being created or destroyed. So what happens? What happens when we have this branching that is taking place? What we will see is that if we have a charge coming here, let's say that charge has a value of 2C. So remember, C is coulomb. And then you will see that before it branches, you have a total of 2 coulomb charge entering, and for the law of conservation of charge to apply, the same charge, we must still have the same charge even after the branching. So you see, charge. So for that to be fulfilled, then it means that a charge will go, it will split, will have a sort of a splitting of charge or a splitting of current in this instance, where a coulomb of charge will go here and another coulomb will go to this branch here, to make sure that we have the total amount of charge entering the branch is the same as the one exiting the branch. But the splitting of the current will depend on the size of the resistor. So for argument's sake, let us assume that these resistors are of the same size, then it will be split in half. So we'll have that coulomb of charge going there and another coulomb of charge going there. So now the total, so we know the total charge entering there is 2C, as well as the total exiting is this Q plus this Q, making it 2C. Because if we were to say, no, okay, 2C is entering, so 2C is also going there, 2C is also going there, then all of a sudden we have 2 plus 2, and then this law is against this law of conservation of charge is not being fulfilled. Now it means that we have now created charge out of nowhere. So yes, to conserve or to go to, what is it? Hey, the English is playing tricks on me now. For this law of conservation of charge to be fulfilled, it makes sense that also there has to be a splitting of current. That is why resistors that are connected in parallel are said to be current dividers. So the current is split between these two branches, this branch here as well as this branch. But then for potential difference, it is the same. It is different. They say potential difference is the same across each of these branches. So now if we were to take a voltmeter and we put a voltmeter here to measure the potential difference in this branch, and we take another one to measure the potential difference here, we would see that the value we get here is the same as the total value, as well as, so all of these values are the same. The value that you get here is the same as this value, is the same as the total in the entire circuit, so between these two terminals of a battery. So they say because energy is not created or destroyed but transferred forward, so it makes sense that energy per unit charge in each branch should be the same. So to kind of review, we're saying that resistors that are connected in parallel, they are not in the same branch as is the case with resistors in series, but you see that they are in different branches. And then the current in those in those branches is split. So the total current is split between the 2 branches or the 3 branches, depending on the number of branches that you have in your circuit, but the voltage is the same. So remember, so I hope everything makes sense. So I was going to say, just remember, resistors in series are potential dividers, while resistors in parallel are current dividers. So yes, this brings us to the end of the second part of our of this video. If you didn't understand something or you'd like more clarity, like I've mentioned in the beginning, please do not hesitate to leave a comment in the comment section. And the next video that I'll be doing, then we will be talking about internal resistance. So you have to keep on the lookout for that video. Remember to subscribe, to tell your friend or anybody who might find this helpful. Then for me, creating this channel was to assist, to be of assistance to people who might be needing this. If you're looking to revise or just to remember what you did in class. I'm not sure when is it that you did this in class, but it might be helpful. And also, as part of this series, I'm also going to be doing questions. So like I said, the 4th video that I will do will just be me doing questions from previous question papers and everything. So yes, thank you very much. See you on the next video. Thank you.